Hello. Today we are going to be going over lesson 2.1.2. How can I measure steepness? Slope. I want you guys to keep some questions in mind as we're working through today. So question number 1, what makes lines steeper and what makes them less steep? Question number 2, how is growth related to steepness? We talked about growth in our last lesson. And question number 3, where is the starting value on a line? And again, that's a repeat from our last lesson. So let's start off with a little warm-up. This should remind you of what we did in our last lesson. The question is, write an equation that represents the tile pattern in the table below. As a reminder, when we write an equation, it's going to take on a format that looks like this. And what we need to do is find some values to put in these two spots here. If you can remember how to do that, go ahead and do that on your own. Hit pause and do it on your own. If you need another hint, stick around and I'll give you a hint. All right, here's my hint to you. If you're not sure what goes where, we want our growth to go in that spot. And we want our starting value to go in that spot. I've got one more hint for you, but if that's enough, go ahead and pause and finish up that equation. All right, here's my last hint for you. When we're looking at a table, we can spot the starting value by looking for 0 in the x value. When x is 0, that y value is always going to be our starting value. In a table, we can spot the growth by looking at how much the y value is changing each time. What I'm seeing here is that the pattern is that I'm adding 5. 2 plus 5 gives us 7. 7 plus 5 gives us 12. 12 plus 5 gives us 17, and so on. That makes my equation y equals 5x plus 2. All right, go ahead and answer number 12 here. Does this relation appear to be a function? And if so, write it in function notation. So remember, we're looking through the x's to see, do we have any x values that give two different y values, any inputs that give us multiple outputs? We don't, so this is a function. So let's write it in function notation. The only thing that changes with function notation is y changes into f of x. So go ahead and write that same equation down, but this time instead of y, give me an f of x. All right, let's go ahead and move forward here. So this is a little bit new. From here, we're going to be looking at a graph, finding the starting value and the growth, and then using those two things to write our equations. We will also be checking to see if it is a function, yes or no. So let's go ahead and have a look. Now remember, the starting value is the y value whenever x is 0. So x is 0 right here, and the y value when x is 0 for this one appears to be 3. So my starting value is 3. To find the growth, we need to figure out how much are we changing our y value as x goes up by 1. Just to remind you from a table, remember, to find the growth, we are looking at how much is the y value changing from one point to the next. So if I go from this point to this point, how much is my y value changing? It's starting at 3 and it's going up to 5. So my y value is going up by 2. So my growth would be 2. So I've got a starting value, I've got a growth. Go ahead and write that equation for me. Can you remember which one goes where? Can you remember which one goes where? Starting value was 3, the growth was 2. So y equals 2x plus 3. All right, is this a function? We could use our handy vertical line test to test this one. I'm going to sweep a vertical line across our graph here. Is it ever touching in more than one spot? Nope. So it passes the vertical line test, which means, yes, it is a function. All right, so as a reminder for this one, the starting value was the value on the line when x was 0. So it's the value right here on this axis, on this y-axis. And then my growth was how much is the y value changing as I go from one point to another. So I want you guys to look at these next two examples and see if you can identify a starting value and a growth value, and then turn those into an equation. So please pause the video now, try these next two examples, and then come back and check your answers. All right, I'm going to give you some hints. If you'll remember, the starting value here was the y value when x was 0. My starting value here is going to be the y value when x is 0. My starting value here is going to be the y value when x is 0. Another hint for you. My growth is how much the y value is changing. Remember, the y value goes up and down. So my growth tells me how much the y value is changing as I move from one point to the next. My growth is telling me how much the y value is changing as I'm moving from one point to the next. So for this one, my starting value would be 9. That's the y value when x is 0. And my growth, as I go over 1, I'm going up 12. So plus 12. And then we can fit that into our equation. Starting value goes here, and growth goes right here. So y equals 12x plus 9. Nice. All right, starting value this time around is this y value. It's not labeled, but I can see we're going 0, 1, 2, 3, 4, 5. This is at 3, so my starting value is 3. And then my growth, again, I've got to kind of count, but how much am I moving in the y direction from one point to the next? I'm going up by 1. So my growth is 1. So that makes my equation y equals something, x plus something. Growth is 1. Starting value is 3. And there's our equation. We probably would not write this 1 in a final version of this equation. We would just write this as y equals x plus 3. But we would know that there would be an invisible 1 in front of this. Keep that in mind. That's going to come up a little bit later. Are these both functions where they pass the vertical line test? Yes and yes. So these are all functions. Okay, if you have any questions on these first three, please put a little star in the margin of your paper. Write that question down, or 1 or 2 words that would help you remember what that question is later so that you can ask your teacher at a later time. And we're going to move on to the next page. All right, folks, you are doing great. All right, let's talk about this thing called slope. So far, we've been talking about growth. Slope is a little bit different from growth. So I'm going to start up here. All right. So let me read here. The graph shows a line for the tile pattern. How is the line growing? That is, how many tiles are added each time the figure number is increased by 1. Explain how you found your answer. I want you to think about this for a minute. And I want you to notice that as we look at this tile pattern, from here to here, I want you to think about what's happening down here. What is this plus 3? This plus 3 is telling us how many new what? It's in the x direction. That's telling us how many new figures. So as I go from figure 4 to figure 7, so I've gained 3 new figures. As I add 3 new figures, I want you to be looking at this. What is this 27? This 27 is in the y direction. That's the number of tiles. So when I add 3 new figures, I'm adding 27 new tiles. So how many tiles am I adding for each of those figures? Take a guess and write your answer down here. I'm adding 27 tiles. And that's while I'm adding 3 new figures. How many tiles for each figure? So I think my answer is 9 tiles per figure. My reason for that is if I take 27 and I divide it by 3, my answer is 9. Why is that working? Well, 27 new tiles altogether, but that's over 3 figures. So if I split that 27 into 3 equal parts, that's what division does for us, we get 9 new tiles per each figure. All right, let's move on to number 15. All right, so these triangles, like you saw in 13 and 14, and as we're seeing right here in 14 and 15 also, these are called slope triangles. So slope triangles, that would be this triangle right here. And slope triangles help us to find slope. Let me read through this. Slope is a measure of the steepness of a line. It is the ratio of the vertical distance to the horizontal distance of a slope triangle. The vertical distance and the horizontal distance. The vertical part of the triangle is called, and this is incorrect, I'm going to go ahead and make a quick correction here. Sorry, I've got a little typo in my notes. The vertical part of this triangle is called change in Y. Vertical goes up and down. Thank you guys for being patient with me. Change in Y. Your notes will not say that because I will fix it before I print it. And the horizontal part of the triangle is called change in X. This little triangle here is the Greek letter delta. So if I read this, I would say this is delta y and this is delta x. So delta y is the vertical part, up and down. Delta x is the horizontal part. Well, it turns out that slope is equal to a fraction made up of those two things. And I want you to think about the last problem. Which one went on the top of our fraction here to find this slope? This 9 is a slope. We put 27 on the top. Is 27 a delta y or is it a delta x? 27 is a delta y, and 3 was our delta x. So it turns out that slope is delta y over delta x. The change in y over the change in x. Now you probably learned this a different way previously, maybe back in middle school. You probably learned this using a couple of R words. Do you remember some R words that go along with slope? Are you thinking about rise and run? Well, these two things correspond to rise and run. If you think about rise, when you rise, you're going up and down. So rise is like our delta y. And when we run horizontally. That would be our delta x. So when you learned rise over run, that's another way to say change in y over change in x. All right, so let's have a look at number 16 down here. And we're going to look at some slope triangles. So they've actually drawn 3 slope triangles, and they've labeled them A and B and C. Let's go ahead and find the slope using triangles A and B. So let's start with triangle A. And for our slope, remember it's going to be change in y over change in x. I'm going to keep writing this down over and over again because that repetition is what's going to help me to remember this over a long period of time. Change in y over change in x. So I'm looking at A. Remember, y goes up and down, so my change in y appears to be plus 6. My change in x is 4. So 6 over 4. And let's go ahead and look at slope triangle B. Slope triangle B is right here. Same thing, I'm going to look at my change in y and my change in x. Change in y over change in x. This time around, my change in y is 3, and my change in x is 2. So when I did A, my change in y over change in x was 6 over 4. With B, it was 3 over 2. It's asking us, what do we notice? I want you to think about this fraction. Would you ever give this fraction as an answer when you're solving an equation? Hopefully not. Hopefully you would think that you might simplify that. There's a couple ways you could simplify it. You could turn it into a decimal just by dividing 6 divided by 4. If you don't know what 6 divided by 4 is, that's okay. Your calculator does. It's 1.5. So my slope here is 1.5. What if I simplify this into a decimal? What am I going to get? What's 3 divided by 2? Oops. 3 divided by 2. Think about what is 3 divided by 2. If you're not sure, your calculator does. It is 1.5. Those are exactly the same values, aren't they? Also, you might be thinking about 6 over 4. You might think about reducing that fraction. That fraction does reduce. There is a number that we can divide both a 6 and a 4 by, and that number is 2. If I divided each of those by 2, 6 divided by 2 is 3. 4 divided by 2 is 2. Wouldn't you know? You get the exact same slope. All right, so I want to ask you a question that's not on this sheet. Do you think it matters where I draw my slope triangle or how big I draw my slope triangle if I'm looking at one single line? Am I going to get a different answer if I draw my slope triangle between these 2 points than I would if I drew my slope triangle between these 2 points? What do you think? I'd say the answer is, so far it seems like the answer is no. I got the same slope for both, 1.5 or 3 over 2. Let's see if that holds out when we go on to triangle C. So in part B, they're asking us to find the slope for triangle C. They are asking us first, we need to figure out our delta y. They didn't give us a number this time around, so we're going to have to do a little bit of counting. So I'm counting spaces here. 1, 2, 3, 4, and that looks like about a half. So I'm going to say that my change in y is 4.5, 4.5. We've already got our change in x, which is 3. So if I wanted to write this as a fraction, change in y over change in x is 4.5 over 3. I have a question for you. Is that the same as what we got for our other slopes on this line? Do you know what 4.5 divided by 3 is? See if you can figure out or take a guess what it is in your head, and then we'll check and see if you're right. 4.5 divided by 3. If you had $4.50 and you split it up between 3 people, how much money would each person have? $1.50, $1.50. 1.5, is that the same slope that we had before? It certainly is. So I asked you a question a moment, does it matter where we measure our slope? I would say the answer is no. I can pick any 2 points that are on this line, find my change in y, find my change in x, and we are always going to end up with the same slope. We might end up with a different change in y, we might end up with different changes in x's, but when we put them into that fraction, that ratio is always going to end up the same. All right, this last one is asking us to draw a slope triangle on the line with a horizontal distance x of 1 unit. I'm going to do it down here because I don't really have space. So I'm going to say my horizontal distance x is 1. And they want us to know what is the vertical distance of that triangle. I'm going to blow this up a little bit. Let's draw it right here. So for this little piece down here, if they said that our horizontal distance is x, what is my vertical distance? I want to see if you can figure this one out. I want you to remember a couple things for me. Remember that our slope is change in y over change in x. Now, I already know that one of those things is 1. Is that the change in y or the change in x? Let's say that's my change in x. And we talked about this just a minute ago. It doesn't matter which 2 points I pick. We should always get the same slope. And the slope that we got each time was 1.5, or 3 over 2. So my question for you is, what do I need to have for my change in y so when I divide it by 1, I get 1.5? Go ahead and take a guess and write it down on your own paper. It would have to be 1.5. Right. So, a couple important things that we talked about today. The big important thing today is this right here. I want you to start thinking about slope as change in y over change in x. I encourage you to write that down every time you're doing a slope. If you do that, that repetition is going to help this stick with you for a long time, and you are going to need this for a long, long time. We will be using this the rest of the year this year. You'll use it extensively next year in geometry and algebra 2 and pre-calculus. This is actually one of the most important parts of calculus, which is coming a few years down the road for those of you who had that route. So big, big, big important mathematical concept. Slope is change in y over change in x. If it helps you to remember rise over run, to help you remember that, that's great, but we want you to start thinking about change in y and change in x. The other important thing that we saw today was that it did not matter which 2 points we picked to find slope. If we're doing change in y over change in x, we may have some different numbers, but our slope that we get as our final answer will always be the same. And this last part is kind of defining what is slope. The slope is how much my y is changing for every 1 unit in the x direction. And this relates back to where we started today with growth. So when we were finding this growth, we were actually finding slope, because for every 1 unit in the x, this is our change in y. All right, thank you so much for your attention.